Alright guys, in this video I want to show you how to do an independent samples t-test. So yet again, I grabbed these examples from those extra practice problems online. So if you want to follow along, that's where they're at. Otherwise you can pause the video and write down anything you want as we go along, or just watch me, right? Whatever sounds good to you. So the practice problems. You will need a calculator, you're going to need your t-table, right? So get all that stuff ready to go. Alright, now let's start by reading the first problem. Hey, go figure, that sounds like a good place to start. Is Facebook making people more honest with their self-portrayals, or is it making people more secretive? We asked 17 people who use Facebook, as well as 18 non-Facebook users, to fill out a survey on honesty and compared their scores to see if there were any differences between the two groups. Okay, so two different groups of people, right? Because 17 people who use Facebook and another 18 who don't use Facebook. So we could say the N of the X, which would be the people who use Facebook since they came first, would be 17. The N of the Y sample then would be 18, which means degrees of freedom of X is 16. Degrees of freedom of Y would be 17, right? Add them together. Your degrees of freedom total is 32, right? 17 plus 16. Okay, what's our hypothesis? Well, they say, is it making people more honest or is it making them more secretive? So they're really looking for both directions here. So we'll say Facebook affects people's levels of honesty compared to non-Facebook users. Okay, something like that. Like I said, they're saying it can go in either direction, so that means it is a non-directional test. Okay, we have two different groups of individuals, completely different groups of people here, right? So that means these samples are independent samples. So it's an independent samples t-test. Now, what's our critical value here? Well, remember, we need degrees of freedom. We figured that out already. We can carry that down if we want. Degrees of freedom total is 32. That's great, because that's that last line on the t-table where we've already gone all the way to 30, and everything past it is equivalent, which means it's actually the same as what you would find if you looked up these cutoff values on the z-table, the unit normal table. So for p equals 0.01 in two tails, we find the 0.01 in two tails. There it is right there. Let's carry it all the way down to 2.575. Right, non-directional, so it's a plus minus 2.575. Do the same thing again, just carry it over now to the other column for when 0.05 is in two tails, all the way down, 1.960. So I'll just write these ones in, 1.960. Then you move over to the other column to get the value for when 0.10 or 10% is divided into 2, and it's a 1.645. Right, so remember, two-tailed tests. Each of these cutoff values talking about a different size piece of each of these two corners. Okay, so that's pretty easy. Let's do the next one. Same kind of idea. A researcher conducts an experiment to determine whether intensive tutoring, covering a great deal of material in a fixed amount of time, so let's come on like that, is more effective than paced tutoring. Right, and more effective. So that sounds like directionality to me. Paced tutoring is covering less material, same amount of time. Two randomly chosen groups, that's great, of 25 students in each are tutored separately and then administered some proficiency test. Okay, so let's write down some information first before we even get to the hypothesis. We've got two groups, each of them have 25. So n of x is 25, n of y is 25, right? That's easy enough. That means degrees of freedom of x is 24, degrees of freedom of y, 24, and degrees of freedom total equals 48, right? 24 plus 24. It says here that we are looking for intensive tutoring being more effective than paced tutoring. So intensive tutoring will result in higher scores on average than paced tutoring. It kind of looks like tutoring. on a proficiency, my handwriting is getting a little sloppy here because I'm going fast, on a proficiency test. Okay, so that is a directional hypothesis. What direction is it? Well, it's saying that intensive tutoring is going to be more effective, so higher scores, higher values, than paced tutoring, which means our x values will be higher than our y values, and our formula is set up as an x minus y, and that means that these will be higher than that, which means we should have positive cutoff values, right? It should be on that side of the distribution. So I said that we've got two separate samples here, right? Two different groups of people, 25 students in each group of tutoring. That means this is an independent samples t-test because our two groups are totally independent of one another. What are our cutoff values then? Well, remember our degrees of freedom is 48, so that's way down at the bottom, past that section that says large, right? Basically the same as it would be for the unit normal table. These are one direction, right? Singular direction tests, one tail tests. So we have to look to see when p equals 0.01 is in one tail. So we take that all the way down to the bottom where it says large here for any degrees of freedom of 30 or above, and it's a 2.327. So we write down 2.327, do the same thing for when p equals 0.05 is in one tail, 1.645, and for when all 10% is in one tail, a 1.282. Okay, so a little bit of practice, some more with critical values, directionality of tests, hypotheses. Now let's do a full-fledged example. Okay, so two samples. Remember, two sample tests are always going to take you a little bit longer because you got to calculate all of those statistics for two samples. The actual t-test part of it's easy once you get to there. So let's start by reading our example and thinking about where we need to go. Okay, in a packing plant, a machine packs cartons with jars. It is supposed that a new machine will pack faster on the average than the machine currently used. To test that hypothesis, the times it takes each machine to pack 10 cartons are recorded. The results in seconds are shown in the table below. Did the data provide sufficient evidence to conclude that, on the average, the new machine packs faster? Here we're also told, perform the required hypothesis test at the 1% significance level, so a p equals 0.01. Okay, so let's talk about what we already know now in this problem. Okay, it says takes each machine to pack 10 cartons. So that's 10 and 10 for each machine. So that's an n of 10 over here, an n of 10 over here, which means a degrees of freedom of 9 for each of these two groups. All right, so we can know that right off the bat. In fact, we can go ahead and write our research hypothesis down here and say something about directionality. So they're saying the new machine packs faster on average. So let's record that faithfully here. The new machine packs cartons faster on average, geez, I'm writing too small, on average than the old machine. Okay, so simplistic hypothesis, the new machine packs cartons faster on average than the old machine. All right, so what does that mean then? If that's the case, that the new machine packs cartons faster than the old machine, that means the length of time it would take to pack things on the old machine would be longer and thus larger numbers. So we would expect the values over here on this side to be larger than the values over here on this side, which means when we subtract x minus y, as the structure of these things goes, we would expect those to be positive values, right? And so we would then expect a positive cutoff. So I'll write positive cutoff here so I don't forget it. Remember, that's a directional test because I'm saying it's faster, and because our independent variable type of machine is basically manipulated between groups. There's no machine that is both an old machine and a new machine. You have different ones. You have an old machine and you have a new machine as separate groups. Your independent variable is then manipulated between groups, right? The design is a between groups design. Okay, so what does it want us to do next? Can we do anything really easy still? Yeah, we can. The type of inferential hypothesis test to be performed then. We've got two groups of people that are entirely independent, right? Or two groups of measurements that are entirely independent because the machines are different machines. So we are looking at an independent samples t-test. It's a 0.01. We said it was directional, and it's a two-tailed test. Excuse me, a one-tailed test with degrees of freedom of 9 in each group. So if degrees of freedom of 9 in each group means if you combine those two groups, your degrees of freedom total is 18. So a p equals 0.01 in one tail with degrees of freedom of 18. So p equals 0.01, one tail. Let's find where that 18 happens to be. And there we go. It is a 2.552. So positive 2.552. What we would say is in this tiny little wedge down here, 552. All right. What else does it want us to do? Calculate the test statistic. Damn, that's a big step. Well, let's go back over here then, and let's calculate some of those values that we need. So let's figure out the average of this packing machines. Let's figure out the average of this packing machine. Then let's figure out the standard deviation or variance of each of those so that we can get to a measure of pooled variance. We can get all the way to the end to our t-test, okay? Because if you remember, here, I'll write it down real quickly on there. Our t formula is going to require us to do a little more complicated thing here. So I'm going to write it down as m, the mean of x, minus the mean of y. So that's easy. Those are just the samples. Then we have to subtract off the population mean of x minus the population mean of y. How the heck are we going to get that? And then you divide all that by the standard error of the difference. But we also said that this formula is testing the null hypothesis, right? And so it's always difference in sample, difference in what we think is in the mean, in the population. Sample average, population average. And so the null is predicting that these populations are the same. They're predicting that the old machine and the new machine are identical and there's no differences whatsoever. So whatever the old machine packs at, that's the same as what the new machine packs at, and so this would equal to this, and thus this minus this would equal 0. We can get rid of it entirely, pretend like you can't even see it, it's not even there. So it's just mean of the sample x minus mean of sample y divided by standard error of the difference. So we'll get to that in a second, but it's basically built on variance, so we need to get variance. Starting first with our sample means. Okay, so let's add all these together real quick. You should get it to be a 432.3, which then means our sample average for the x variable is a 43.23 because our sample size was 10. Okay, so now x minus x bar. All right, let's go. All right, now we need to square them. All right, so add all those together, do it twice, make sure you got it right. All right, sum of squares of x then should come to 5.05. Okay, now let's go over to the new packing machine and do the same thing. In this case, you add all those up together, you should come up with a sum of 421.4, which means our y average over here would be a 42.14, right? It's always easy when the sample size is 10. All right, so now we need to do y minus y bar. Okay, now we need to square all of those values, right? So the y minus y bar squared. All right, now sum them all up together, right? Again, double check it. Sum of squares y should give you a 4.22. All right. So now we have sum of squares x, we have sum of squares y. We need to get to variance. So I am going to grab a new sheet of paper to do that, okay? So let me write down these values. Sum of squares x is equal to 5.05. Sum of squares y is equal to 4.22. Now, our sample size of each of these is a 10, so I'll write that down once. Remember, in order to get to variance, it's just the step before standard deviation, so we call it s squared of x, right, would be equal to 5.05 divided by n minus 1, so 10 minus 1, so 9. Okay, when we do that, 5.05 divided by 9, we get a value of 0.56. Do the same thing over here for y. 4.22 divided by 9 is equal to 0.47. Remember that if we were doing standard deviation, we'd take the square root of this, but we need to do pooled variance next, so we don't want to take the square root of that. In fact, let's go ahead and just use this piece of paper right here, now that we have it out here, to get pooled variance. So how do you do that? Pooled variance requires us to use both of these variances and combine them in some way. So what you have to do is take degrees of freedom x over degrees of freedom total and multiply that times the variance of x, and then add that times, again, the degrees of freedom y over degrees of freedom total times the variance of y. Well, that's easy. We know all that stuff, right? So degrees of freedom of x is 9, because there were 10 individuals in that group, 20 total individuals, so 9 over 18 would be our degrees of freedom x over degrees of freedom total. 0.56 is our variance for x, so we're going to add that then to the same thing, because we had the same sample size over here, times the variance of y. So this comes to 0.28 and 0.235, which rounds up to 0.24. So then when you're done, you get 0.52. All right, so this is pooled variance, okay? Pooled variance. Now, next step is to take pooled variance and divide it by each of the sample sizes. Now, again, our sample sizes were the same, so that makes it nice and easy. We just take 0.52 and we divide it by the sample size of x. We take 0.52, we divide it by the sample size of y. They were the same. Now we're going to add them together at the end too. So this goes down to 0.052 and 0.052, and they add together to 0.104, which we're rounding out to 2 decimal places, so 0.10. Okay, now the last step in creating standard error of the difference is to take the square root of that value. So the square root of 0.10 gives you 0.32, and that is our standard error of the difference. All right, so now that we have that, we can calculate our test statistics. We can skip ahead to that page that told us it wanted us to do that anyway, now that we are ready. Okay, so here we are, calculate the test statistic. We already looked at our t formula. We know that it's mean of x minus the mean of y, right? So x bar minus y bar, or mean of x minus mean of y, however it's written, divided by standard error of the difference. Okay, so what were our sample means? Our sample mean for x was 42.23. Our sample mean for y was 43.23, I got that wrong there. Divided then by the standard error of the difference that we just calculated, 0.32. Okay, so you should have 43.23 minus 42.14 divided by 0.32 as the structure of your t equation. Divide all that out, calculate that, you get a 3.406, which rounds up then to a 3.41. All right, we have our test statistic. Now we need to make a decision. What was our cutoff value? Can you recall what we determined for that? Right? It was a 2.552 because we have a directional test with 18 degrees of freedom. So, and if we draw our big distribution here, and we say there's our cutoff, and all that is where we want to find our test result to say it's less than likely to be due to chance, and in fact due to something else. 2.552, and look at that, 3.441 definitely falls into that shaded region. So we have a statistically significant difference. We can reject the null hypothesis. And because it was a directional test, we know what direction it came in since it passed that cutoff. So we can say, in fact, that, let me write this down as our decision. New machines pack cartons faster on average than old machines. And that's it. That's the independent samples t-test.